All right, so last night for homework, you were asked to find the slant asymptote. Again, I didn't ask you to graph it, but I'm going to graph it as we go along, just to see what's going on. Let me put... all right, so we have the function x squared plus 2x minus 8 over x plus 2. All right, so the first thing that we always want to do is to try to simplify it, to see if we have any holes, anything, removal of discontinuities, things like that. And it helps us later on when we're finding our different parts. So the denominator is a linear function. We can't touch that. That's going to stay x minus 2, or I'm sorry, x plus 2. The numerator, though, we can break that up. Factors of 8 are 2 and 4. So we have a negative 8. So one of our factors has to be positive. One of them has to be negative. It's a positive 2. So that means the larger number is going to be positive and the smaller number is going to be negative. So although it looks like we might have common factors, okay, they are different because that is x minus 2 and x plus 2. So no removable discontinuities, no holes in our graph. The first thing you are asked for is the y-intercept. Okay, so the y-intercept, we can plug in 0. So when we plug in 0, okay, I'm going to use this first one because these two terms will go away. This term will go away. We get negative 8 over 2, or negative 4. All right, so somewhere down here at negative 4, let's say that's negative 4, I have my y-intercept. Right? If you gave it to me as a coordinate point, it would be 0, negative 4. Okay. The second question, I asked you for the x-intercepts. Now we're looking at the numerator here, and I'm going to go ahead and use that factored version because it's going to be simpler. Okay, I have two x-intercepts at x equals positive 2 and x equals negative 4. All right, or the point 2, 0, negative 4, 0. All right, so there's one, and then there would be the other. All right, so that looks kind of nice. We got a few points. All right, sometimes we can't find any, right? Sometimes it doesn't have any intercepts, so it's nice to have a few. So next we had our vertical asymptote. So remember, for that, we are going to set the denominator equal to 0. So our vertical asymptote is the line x equals negative 2. And so if you were sketching the graph, you would put a dotted line, an invisible line there at x equals negative 2. So again, this is good. We got some points on both sides, right? So I don't have to do any testing later. Hopefully everything kind of fits where it's supposed to be. So our last step. Now, here I told you it was a slant asymptote, but you may just be asked, if you're asked to graph this, you won't be told it's a slant asymptote. You have to recognize that it's a slant asymptote from our rule, right? Our numerator degree is greater than our denominator degree. Right, so we have to set up our long division. Right, so we have x plus 2 divided into x squared plus 2x minus 8. So our long division, how do I get an x to look like an x squared? Well, I multiply it by x. So I get x squared plus 2x. When I subtract those cancel out, right? And we're just left with the negative 8. So that's my remainder. Now remember, I don't have to do anything with my remainder. All right, so here, that's my slant asymptote. Okay, the line y equals x. All right, so that should have been your answer for your last one. Okay, if you just said x, that's okay. But it is an equation, right? Equation needs both y and x, so the actual answer would be y equals x. So just going back up to our sketch, right? Y equals x would be a line that kind of cuts through like this. So I have my one side, I would go through those 2 points, and then I know that this point's over here, so I would come up like that maybe. Right, so we have our graph of our hyperbola. Okay, it's the wider side, it's not the shorter sides. And that's what our graph would look like. Any questions?
Can we just try one more problem?
Yeah, sure.
Or I mean, it's fine. I could just look it up on YouTube.
No, we'll go over one more. Let me find one. All right, let's see. What can I do here? Now, do you want to go over what part specifically, like the slant asymptote part, or just kind of the whole thing that we did?
The slant.
Okay.
Yeah.
All right, so let's take a look at our function f of x equals 2x squared minus 5x plus 5 over x minus 2. All right, so just for, since we're talking about asymptotes, I'm going to quickly do the vertical asymptote. Our denominator, x minus 2, we set that equal to 0. Oops, no. So we get x equals 2. All right, so at x equals 2, we have our vertical asymptote. Okay, so again, horizontal, there is no horizontal because n is greater than m. But again, that tells us that we have to divide for slant. So we set it up, x minus 2, 2x squared minus 5x plus 5. Right, so I'll do it the other way that we did when we were doing long division. So my first term here is 2x squared. I'm dividing that by x. So what do I have left over? Okay, I cancel out one of the x's and 2x. So 2x is what's going to go up here. Now when I multiply, remember we're distributing the 2x to both terms. So I get that 2x squared and then minus 4x. So we subtract. They eliminate. Negative 5x minus negative 4, that turns to plus. So I get a negative x there. And then I bring down the plus 5. So now I have a negative x. I'm dividing that by x. Well, that's just going to be negative 1. So in all honesty, I can stop right here. Okay, I don't have to go further. It's going to have a remainder. The remainder doesn't really matter for the slant asymptote. So here our slant asymptote is the line y equals 2x minus 1. So you go down to negative 1. You have a slope of 2, so it goes up 2 over 1. Okay, so we're going to have some kind of asymptote like that. So here, okay, it's a little different because now we just have the slant asymptote lines. So if you're in a situation like this, well, the numerator looks a little hard to kind of deal with for our x-intercepts, but a real easy point you can plot is your y-intercept. All right, so plug in 0 for x, and we get negative 5 over 2, or 5 over negative 2. All right, so that's going to be down here. So you know one part of your graph is going to be this skinny little leg here. So that means the other part of your graph will be up here. All right, so remember that these asymptotes are kind of shaping what the graph looks like. All right, and again, we only have this slant asymptote because we can actually divide, right? And then when we divide, that resulting equation is the line that you can't cross. That's your slant asymptote. Did that kind of clear up any issues? Did it make it worse?
It's good now. I was just confused a little bit, but now it's good. It's
Okay.
good.
On which part precisely, or was it just kind of a general thing?
It was just I got confused because I was supposed to multiply. Like when I'm simplifying the top, but that was it. I looked at my mistake already.
Okay. Okay. Yeah. Right. So sometimes, if you get confused with that, do the simplification for like your intercepts, but then doing the rest, you're going to go back to your original function. Okay, especially for the slant asymptote, you can't really use the simplified version. And usually with the slant asymptote, you won't have a simplified version.
You can raise it.
All right. Any other questions or issues or comments before we move on? Because we're starting a brand new topic today. All right. So we'll see how much time we have. Today might just be like an introductory lesson. Exponential functions. Okay, so our formal definition, an exponential function, f, with base a is denoted by f of x equals a to the x power. All right, so now we're taking a look where our exponent is a variable. All right, so we have a few conditions that we need to place. A is going to be greater than 0. All right, so it's not going to be negative right now. A can't equal 1 because 1 to the x is just 1. That's a constant function. And then x is going to be a real number. So x can be almost anything except imaginary numbers. Okay, your complex numbers. So exponential functions are used a lot in life, in real world stuff. It models, well, actually, let me ask you guys, what science are you guys in right now?
Biology.
Biology.
There's also physics.
Physics, okay. Did you guys take chemistry already?
Yeah.
Yeah.
Okay. All right. So good. So actually in biology and in chemistry, we use exponential functions. I mean, obviously physics kind of is everything. So yeah, you're going to see it there. But in biology, when we're talking about things like population growth, okay, so like cells and bacteria that are doubling, okay, that's an exponential function. In chemistry, I'm not sure if you've talked about it yet, but there's something called half-life. And that has to do with radioactive things decreasing. Like, you know, if you have a radioactive bar of uranium, due to chemical processes, that uranium will eventually disappear, right? It shrinks and it shrinks. It loses its radiation. And that's called half-life, and that's modeled by exponential functions as well. So there's a lot of ties into, you know, the science community with exponential functions. So let's see. I get 10 minutes. All right. Okay, so one of the things is how to calculate it. So if you're using your phone calculator, I don't think mine has it because I don't have an iPhone anymore. Okay, so I don't know if you're going to be able to see this. That's really crappy quality. But here, it's a little caret that's pointing. It's an arrow that points up. That's not it. It's over here. Yeah, sorry guys, that's real crappy. It's just a little symbol that looks like this. Okay, that means exponent. So if you type in your calculator 2 caret 10, that would be 2 to the 10th power. You might also see, if you have an iPhone, a button that looks like x to the y, like that. So you would type in the base first, then you would hit this button, xy, and then you would plug in your exponent, whatever that may be. All right, so just be careful when you're calculating these. There's different ways. You can use an online calculator. Excuse me. And again, to punch in the operation, you would use the up arrow. I don't know if you've seen me when I type the equations into the online calculator when we're graphing things. Okay, you know, I type x caret 2, and that gives me x squared. Right, so that's just telling you you have an exponent. And this button is on the main calculators that we would have if we were in school. Okay, it's over here. So if you're not doing something that's simple like x squared, or you know, like 5 squared, you would use that caret symbol, right? And we would also use that to plug in the actual exponent, right? So I could graph what 2x looks like, 2 to the x power, what that looks like with that caret button. Okay, so if you hear me say caret, I'm not talking about the actual, you know, Bugs Bunny carrot. I'm talking about that symbol. So let's look at the graph. So the graphs of exponentials are pretty unique. We're going to take a look at our most basic one, 2 to the x. So we're going to do it old-fashioned. We're going to make a table, and we're going to plug in. Now, I'm going to start over here with my positive numbers, and we'll graph it as we go along. All right, so when I plug in 0, Anything, when I raise anything to the 0 power, 2 to the 0 power, 10 to the 0 power, negative infinity to the 0 power, it's always going to be 1. Okay? So our exponential functions, as long as it's just a to the x and I don't have anything, fancy after it, adding or subtracting or anything on the outside, your y-intercept will more than likely always be 1. When I plug in 1, 2 to the first power, well, that's just 2, right? So we go up. So we're increasing, right? When I plug in 2, 2 squared, well, that's 4. So not only am I increasing, but the increments that I'm increasing are also increasing, right? It gets a little steeper. When I plug in 3, 3 squared, 2 to the third, I get 8. So that would be kind of, off the charts here. So when we're talking about things like, diseases, when you hear the term exponential growth gets out of hand very quickly. Okay. Let me just see something real quick. Yeah, if I go up to 2 to the 10th, 2 to the 10th is over 1,000. Okay, so it's not very far down this way on our x parts, but it shoots up very, very quickly. Okay, so exponential growth was something like, bacteria and infections is kind of bad, right? But that's kind of how it happens, right? If you're sick and you give it to 2 people, within, a few days, the people that are sick are going to be astronomical, right? If it's not handled correctly. Now, looking at the negative ones, when I have a negative exponent, okay, x to the negative 1, what that tells me I'm doing is I'm taking the reciprocal and I have 1 over x. So if I have 2 to the negative first, that's going to be 1/2. Okay, so on this side of my graph, on the left side of the y-axis, okay, it's getting smaller as we go down to the left. If I have 2 to the negative second, well, that's telling me I have 1 over 2 squared, which is 1/4. So even skinnier or even smaller, right? And the whole left side of our graph has that downward trend. But what happens is we're never going to cross this x-axis. I will never plug in a number into this exponent to make this negative. Okay, I can plug in negative 1,000, and that would be 1 over 2 to the 1,000th power. That would be a very, very, very tiny fraction, 0.0000, who knows, right? But it's never going to cross this axis, all right? It's never going to go below the x-axis. So that brings me to 2 points, and this is what we'll finish off with. Exponential functions, normal exponential functions with this form, again, if I'm not, subtracting 2 from it or something, will not have an x-intercept. Okay. And I forgot what the second part I wanted to say was. Crap. I lost my train of thought. Give me a second. Nope. It's gone. Oh, no, I remember. Okay. So the last thing I want to talk about is, okay, for most of our basic exponential functions, the domain, okay, as we said before, okay, the domain is all real numbers. I can plug anything in here. I can plug in the square root of 2. I can plug in pi. Okay, as long as it's a real number, I can plug it into x. The range Okay, y is just going to be greater than 0. Again, it will never be equal. Okay, or we can say, if we're using interval notation, 0 to infinity. Here, interval notation, we would have negative infinity to positive infinity. Okay. So those are two important parts. All right. Any questions about the basics of exponential functions?